Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside as we jump into the Chapter 6 test in Cumulative Assessment in the Big Ideas Math Integrated Math 1 textbook. So, this is on exponential functions and sequences. The Cumulative Assessment can take anything from Chapters 1 through 6, all things algebra-based. Now, that's worth mentioning because Chapter 7 is statistics-based, and Chapters 8 through 12 are geometry based. So this is our last thing that you get to see that's like fully algebra invested. So sad to see that go, but it's time to move on with these things. It is integrated math after all, not just algebra. Download things down below if you'd like to. Description section down below, you can find the PDFs of the Chapter 6 test, of the Cumulative Assessment, as well as graph paper that I'm going to be providing, and grab your own graphing calculators. I'm sure we're going to be needing it. Without further ado, 14 questions in the Chapter 6 test, 9 questions in the Cumulative Assessment. Let's go ahead and get started on them. We have numbers 1 and 2 where we have to write and graph a function that represents the situation. So on number 1, it says your starting annual salary of $42,500 increases by 3% each year. I'm looking at an initial value of $42,500, and increasing 3% each year, we add it to 1. 1 plus 0.03, that's the decimal equivalent. It's 0.03 to the t power. That ends up being the function for that thing. Now, they're asking us to graph it. That's not one that I would normally do by hand. Probably, are they really asking us to graph this? I'll probably use a graphing calculator for this. It'll probably even look pretty linear, all told. Let's check this one out. So if I did 42,500 times 1.03, and I have to do the x power, understand that that's your y-intercept at 42,500. So even if I'm going to go 10 years and see how that looks, but let's go up to, 50,000 and let's see what's going on there. But from here, it's going to look pretty linear. Oh, yeah. Let's go up to maybe 60,000 or so, and I'll zoom out on Y. Yeah, let's just go 70,000 just to give it a look-see. So for the first 10 years, it's looking like this, and make no mistake, guys, this is a curve. It's not linear. I don't know if there's any way you can tell. If someone asks me, is that linear or a curve? I understand. I might say linear as well, but that is a curve. If I zoom out more, actually, let's keep this graph here, and I'm going to provide this one on my paper on this other side here. If I did zoom out more, however, you would be seeing, like, let's say we did this thing. What was this about? Starting salary? Let's say I worked in the company for 40 years. For 40 years. Now we're going to look at higher amounts. Let's go to 200,000 bucks. Hopefully we see more of a curve here, right? This thing increases a little more over time. Now this time I can see the curve aspect, right? So it's not truly linear. You're making more each year than you were the previous years, 3% more, right? So there is a curve involved, but that's a little too much to be looking at as far as the graph goes. Let's look at just the first 10 years. This was from 0 to 10. And then this was from 0 to, I can't remember now, 70,000, I think. So there's the idea of the graph. This is 42,500 right there. There's the graph. Okay, number 2. You deposit $500 in an account that earns 6.5% annual interest compounded yearly. So compounded yearly means there's no change in what we do on that n. N would be 1 in this case. It's not like compounded quarterly would be 4, monthly would be 12. So 500 is the initial amount. 6.5% is an addition of 0.065 to 1. And again, we're compounding yearly, so this is still to the t power as a function like that one as well. And I guess I'll use the graphing calculator for that one as well. So this one, $500, that's our y-intercept this time. And then 1.065 to the x power is what we're looking at here. This is going to be a lot less again. Let's go another 10 years and take a look at what's going on there. 500. I don't think it gets to $1,000 here. I don't think we're going to double our investment over the course of that time. Oh, we might. It still works out as a graph for me, honestly. So with this graph, just copy and paste that. It's actually a good look. So this is the story of a graph. 0 to 10 years. And then $0 up to 1,000. And this is the 500. It is a curve. It's not a line. It's a curve. Slope curve as we go. Okay, interesting that we did those graphs. Not the way that I would do the graph normally, right? It's just the numbers aren't really set up for me to do that with respect to the table and such. You can use a table. I'm refraining. Numbers 3 and 4, tell whether the table of values represents a linear or exponential function, and then write the function. So we're looking for if there's a common difference or ratio. Doesn't look like there's a neither case, so it is one or the other. Now x is increasing by 1. We're all good there. It's all about what y is doing. This is a constant increase of 4, which means it's a linear function. So up 4 over 1 in the way of a slope, our slope is 4. The y-intercept is the value of y when x equals 0, which is negative 8. So it is a linear function. And the equation would be y equals 4x minus 8. That's what I'd be using for that in terms of how that's working. Remember, it is over 1. That's what's happening. Number 4, I assume would have to be exponential, right? We need an exponential here. And it looks that way. If you don't know what you're multiplying by, remember you can divide a value by the one before it. X is increasing by a constant 1, so that's all good there. But what is, 16.2 divided by 5.4 or 0.6 over 0.2? Well, it's the same thing as 6 over 2. It's 3. So we're multiplying by 3 each time. That makes it an exponential function. So that ends up being your b value, your growth rate. Your a value is your y-intercept in this case when x equals 0, and that's 1.8. So being an exponential function, we're going to use the equation y equals ab to the x power. This will be y equals 1.8 times 3 to the x power, like that. Numbers 5 and 6, they say write an explicit and recursive rule for the sequence. That would be something you'd see out of section 6.6. So we're kind of just moving on up in the world. I'm going to write out the sequence as like a list here. So -6, 8, 22, and 36. And it's all about what's happening here. It looks to make a common difference of 14. Yeah, if I'm adding 14 each time, it's going to be arithmetic. And being an arithmetic sequence with said common difference, we need to know the two following things: the first term and the common difference. And we can use those for our recursive rule. Recursive rule being you take the previous term and you add 14 to it, starting from -6. And the explicit rule, which we can simplify, but the explicit rule being where we find it based on the first term and we add our common difference n minus 1 times. Now, when simplified, this will look like distribution, and then combined like terms, we'll get a sub n equals 14n minus 20. So there are two for an arithmetic sequence. I'm expecting a geometric sequence next to number 6, and it looks so. On number 6, this geometric sequence is unique in that there's decay. The numbers are shrinking as we go along, but that doesn't mean division to us. It just means multiplication by a fraction, right? And in this case, 400 to 100, that's dividing by 4 or multiplying by 1/4. Oh, I wasn't copying and pasting. I was writing a list. So 400, 100, 25, and 6.25. You can bet that's 25 divided by 4 as well. So times 1/4 the entire way through. That is our R value. So our first term is 400. Our common ratio is 1/4. So as a recursive rule, we'll be saying the value of the nth term is 1/4 the value of the previous term, starting from 400. And in the explicit rule, no simplification needed. Once we start writing this, we start with 400. Oh, hold on, a sub n. A sub n equals 400 times 1/4 to the n minus 1 power. That's all we had to do for these problems, right? Write an explicit and recursive. Yep, that's it. Okay. Number 7. Number 8, solve the equation, check your solution. So on number 7, we have 2 to the x power equals 1 over 128. Now, the first thing you might do is say, can I represent 128 as 2 to some power? The answer is yes, it's 2 to the 7th. And 1 over 2 to the 7th can be rewritten as 2 to the negative 7th. That's how negative exponents work. We match the bases, we can set the exponents equal to each other, and that actually solves for x. We get -7. It says check your solution. I mean, try 2 to the negative 7th. You get the equivalent of 1 over 128, so I'll leave it. This next one might be a little bit more worth checking your solution just because you have different bases to begin with in this set. Because there are x's on both sides of the equation, I should say. Is that a plus? Yeah, 16. Okay, on this one, 256 is a power of 4, so is 16, but 256 is also a power of 16. I can just rewrite this one as 16 squared and leave the other 16 as is. That would be perfect. So 16 to the 3x minus 1. 2 distributes into the x and 2, and you get 16 to the 2x plus 4 power. And now that I have matching bases, I can set the exponents equal. So again, 256 and 6 are each powers of 4. They're powers of 2 as well, but do the largest base if you can. In this case, that'll be 16. That keeps these numbers smaller. If I subtract 2x from both sides, I'll get x. If I add 1 to both sides, I get 5. So I'm just going to write that as like that. X equals, oh, you can't see that. X equals 5. I'll write that over here. I'll use this one as my snapshot, my thumbnail. All right, there we go. Okay. Number 9. Graph f of x equals 2 times 6 to the x power. Compare the graph to the graph of g of x equals 6 to the x power. Describe the domain and range of f. So this one I will graph in, I still won't use a table, but I'm not going to use the graphing calculator. We've seen this already based on the previous tables. Not that I'm going to use one, but no. Copy this, please. But there we go. What was I going to say? 2 is the y-intercept. 6 is the growth factor. I have a horizontal asymptote on the y-axis. X-axis, excuse me, on y equals 0, like so. I'm multiplying by 6 each time, starting from 2 on that y-intercept. So here, 2 times 6 is 12. 12 times 6 is 72. I have no intention of fitting that. I can divide 2 by 6 and get 1/3. Divide that by 6 and I get 1/18. Very, very small. Very, very small. So you get an exponential function. It's a positive exponential growth function, like so. Approaching the asymptote. Never quite hitting. That means it never hits 0. That's part of our domain range stuff, by the way. Domain is all real numbers. Range is y is greater than 0. Now we got to compare it to the graph of g of x equals 6 to the x power. The difference is, in this case, this would have a y-intercept of 1, because 6 to the x power is 1 times 6 to the x power. And then times 6 is 6, and times 6 is 36. It's always half the size of these other ones at the same x values. When this x is 1, y is 6, whereas when the other one's x is 1, y is 12, right? And then 2 versus 1, etc. So here's g of x, whereas here we have f of x. So the graph of f, it's a vertical stretch by a factor of 2, right? The graph of f, that's just, I mean, that's the one difference that's in this equation, whereas g of x is the 6 to the x power. There's a 1 in front versus the 2. Okay. Numbers 10 and 11. It says, determine whether the function represents exponential growth or exponential decay. Identify the percent rate of change. On number 10, we have y equals 1.7 times 1.09 to the t power. Now, the 1.7 has nothing to do with the growth or decay. It's all about this guy right here, which is 1 plus 0.09. We're adding 9%. That means this is 9% exponential growth. It's kind of two answers in one. It is exponential growth and of 9%. Number 11 is written as a fraction for that, I don't know if you can call it the b value anymore. They call it 1 plus r or 1 minus r. 1 plus or minus r. This is a 1 minus r in this case because 1/3 is indeed less than 1. How much less than 1? It's 2/3 less than 1. This is kind of an interesting fraction. We normally don't deal with it in this sense, in that its decimal is a repeated value. You know, this is 1 minus 2/3 being the 1 minus r. So, but what is 2/3 as a percentage, right? 2 divided by 3 is 0.6 repeating. That makes it 66.6 repeating percent, 6.7, whatever you want to say. But this is decay, exponential decay, I'll say. This is how much value is lost. If you lose 2/3 of something, you're losing 66.6% of it. Repeating, of course. Okay, number 12. The first two terms of a sequence are 3 and negative 12. Let a sub 3 be the third term when the sequence is arithmetic, and b sub 3 be the third term when the sequence is geometric. Find a sub 3 minus b sub 3. This is the kind of question you only see on the chapter test. You don't tend to see them in the normal problem sets or anything like that. If this was an arithmetic sequence, you're looking at a sequence that is, you know, whatever. Well, we only need the third term, huh? So the third term, when it's arithmetic, I'll just say A is this list and B when it's geometric. Here we're subtracting, it looks like 15. So another minus 15 there is negative 27. Now, the B value, B sub 3, we're going from 3 to the negative 12, which means we're multiplying by something. In this case, we're multiplying by negative 4. So we got to do another times negative 4 here to get this value, and that would be positive 48. So we have, they want A sub 3 minus B sub 3. A sub 3 minus B sub 3 is negative 27 minus 48, which I believe is negative 75. So that's everything in that nutshell. You see, two terms alone don't represent an arithmetic or geometric pattern. You really need that third term. In some cases, maybe even the fourth term. But the two terms alone can be, are we subtracting 15 or are we multiplying by negative 4 or something else? Just couldn't tell. Number 13. At sea level, Earth's atmosphere exerts a pressure of 1 atmosphere. That's the unit, atmosphere. Atmospheric pressure, P in atmospheres, decreases with altitude. So the higher you go up, the less atmospheric pressure there is. It can be modeled by that equation. I probably have to write that. 0, don't really need the parentheses, but 99988 to the A power, where A is the altitude in meters. So as the altitude increases, you get slight change in P, which is the atmospheric pressure. Identify the initial amount, decay factor, and decay rate. So part A, the initial amount would have been the number in front of here. That's 1. Even though there aren't parentheses there, I could wrap it around and put that 1. So 1, how do they do? Is it ATM? I'm going to put ATM as the thing. 1 ATM is the initial amount. It asks for what? Decay factor and decay rate. Decay factor is what we're multiplying by. So decay factor, I'm going to put as 0.99988. Decay rate is how much we're losing as a percentage. So 1 minus this number is the decimal equivalent of it. That's 0.00012, I think. So as a percentage, 2 decimal places over is 0.012%. 0.012%. That's our decay rate. So boom, boom, boom. This is initial. Part B, use a graphing calculator to graph the function. Use the graph to estimate the atmospheric pressure at an altitude of 5,000 feet. So, okay, let's go to the graphing calculator. So we'll type in 0.99988 to the x power. We'll have to extend this out to, I'll just extend it out to 6,000 so I see 5,000 in my view. This goes from 1 and upward, probably not much. No, it goes downward, from 1 and downward. So let's just start at 1 and go downward towards 0 and see that decay. So 5,000, probably somewhere around here. Now, I'm going to actually use my value feature when I type 5,000 here. You can also find it in the table. And you get around this value here, this 0.5487, etc. I don't know how many decimal places they want. I'm going to use 3. So around 0.549 atmospherics. Atmosphere. I don't know what the actual name of it, just atmospheres, I guess. So let me copy and paste that one in. Because they did say graph, so there's our graph. And then P of 5,000, the pressure, is around 0.549 atmospherics there. That's at 5,000 feet. 5,000 feet? Is that what they said? 5,000 meters. Oh! 5,000 feet for 5,000 meters. Hold on a second. A is the altitude in meters. Altitude of 5,000 feet. Oh, timeout. Let's change that then. Let's do, what's that conversion, feet to meters? I could do it to inches, inches to meter, feet to meters. So 5,000 feet is 1,524 meters. So let's do that one again. That's 5,000 meters. I'll leave that up just in case maybe there's a typo there. But P of 5,000 feet is equal to P of, what did I say? 1524. 1,524 meters. Okay, so that, I'm going back to the graphing calculator for that. 1524. That's around 0.833. 0.833 atmospherics. So assuming I read it incorrectly the first time, then this would be the answer. If I read it, I don't know if that was the answer. So there's one or the other. That's 5,000 meters. Here's 5,000 feet. Okay. Number 14. You follow the training schedule from your coach. Right. Where is it? Oh, I had to move this. This is down below. Okay, it's right here. Okay. Write an explicit rule and a recursive rule for the geometric sequence. Day 1, term 1, we're going to run 1 kilometer. Then each day we're going to run 20% farther than the previous day. So let's write the rules first before a sequence. Your recursive rule would be you start with 1 and then you increase another 20%. That's 1 plus 0.2. 1.2 times more than you did before. So there's the recursive rule. This is part A, by the way. The explicit rule is a sub n equals, you start with 1 and multiply by 1.2 to the n minus 1 power. So basically that, literally. Notice I didn't even put the 1 here. That's not a requirement. It doesn't change how your answer is going to look. So I'm just going to write it like that. It'd be the best appearance to me. Part B, what is the first day that you run more than 2 kilometers, more than 3 kilometers? Well, I don't know if they want you to do this in terms of like using the calculator. I mean, I'll use the calculator for the equation, but like, I don't know if we're trying to solve an exponential equation using the calculator or what. I can do the 1.2 to the, x minus 1 power here. And I can use the table, for example, and we could say on what day we go beyond 2. The 5th day is the first day. So on day 5, we go beyond 2 kilometers. Day 5 is more than 2 kilometers of running. So I wrote like that. More than 3 kilometers is day 8. So almost day 7, but day 8. So day 7, we're getting really close, and day 8, we fly past it. You can see 20% more each time, man. It increases pretty fast over that time, like that. Look at that now. Man, I don't know. It's a lot of kilometers. We're marathon running, baby. Day 8. Day 8. So here we go. Day 8. Part C. What is the total distance that you run in the first week? Round your answer to the nearest kilometer. So now we're actually going to be adding all those things up. This is what's known as a geometric series. There's actually a formula for it, which I could even run into with you as well. I'll kind of show you it after we do this. So I'm going to write in these numbers. They're from this table right here. Actually, I'm going to copy paste these numbers. So the first week, they're talking about these first 7 days, I assume. So I'm copying, pasting it. Looks like that. Okay, so we're going to do this plus this plus this plus this, etc. So you can do all those. I'm going to do that in the calculator right now, so give me a second. 1 plus 1.2 plus 1. Now these have some rounding to them, I'm sure, once we're hitting some of these numbers here. 736 and 2.483. But when we round to the nearest kilometer, I'm sure that we'll get the same answer no matter what I do. There's enough precision in my calculations that we're good. So I have 12.9159. 12.9159, which is also about 13 kilometers total after week 1. Now, you won't learn geometric series until IM3. So what I'm going to tell you here is probably not worth your while. You can move on to the cumulative assessment, or you can stop the video, depending on you can do whatever you want. But this part is just superfluous. We're going to get to the same answer on here. There's a formula to find the sum of the first n terms of something. You take the first term, multiply it by 1 minus the common ratio to the nth power, that being the number of terms, over 1 minus the common ratio, like that. A little crazy looking. So the sum of the first 7 terms, you take 1 times 1 minus 1.2 to the 7th power, all divided by 1 minus 1.2. Crazy looking, right? If I go to the calculator for that one, well, let's clean some things up, actually. 1 on the outside is doing nothing. This is 1 minus 1.2 to the 7th power still. I'll leave that up there. And this is divided by negative 0.2, right? So let's try that in the calculator. We'll do 1 minus 1.2 to the 7th power, all divided by negative 0.2, like that. And take a look. We still get that same number. I mean, there's a little more precision. That's the exact answer. But you can see that we still get that same answer. So pretty cool. 13 kilometers. Something you'll learn in IM3 and you'll actually apply in IM3. That would be a faster way to do things, especially when you have multiple terms like that. That's for geometric sequences. Geometric series, I should say. Okay, guys, we're going to go to the cumulative assessment. 9 problems on these. They can hit anything from chapters 1 through 6. I'm prepared and ready to go. If you are as well, let's get the slides ready. Here we go. Number 1 says fill in values to write a linear function g so that f of x equals g of x has 2 solutions, x equals 2 and x equals 4. We have an equation that says f of x equals 1/4 times 2 to the x power. What I want to do for that linear equation is write something that has these solutions, which means it has those values. Let's check out what f of 2 equals. That's 1/4 times 2 squared, which is 1/4 times 2 squared is 4. 1/4 times 4, which is 1. That means there's an ordered pair that's 2, 1. We need to make sure our g of x hits 2, 1. There's also an f of 4, which is 1/4 times 2 to the 4th power, which is 1/4 of 16, which is 4. So there's also an ordered pair that's 4, 4. We need our g of x equation to have some mx plus b, where our m and b represent having that slope and y-intercept. So the slope is based off of taking the y2 minus y1 over x2 minus x1. That's 3 over 2. The b value can be found, now we're at g of x equals 3/2 x plus b. The b value is found by substituting. You can use point slope form or slope intercept. I'm going to use slope intercept form. You can substitute like 2 for x and 1 for y, for example, and find b. Like so. 3/2 of 2 is 3. And b is negative 2 when all is said and done there. So our final equation for g of x should be y equals 3/2 x minus 2. This is the one that would pass through those. So find the m and b there. Boom, those would be the 2 solutions. Because they need to intersect at those same places, right? That's the point. It needs to cross through those 2 places just like this one does. That's number 1. Number 2 says the graph of the exponential function is shown, and they want you to find f of negative 7. In order for me to find f of negative 7, it's best if I come up with that equation and then just substitute negative 7 for x. I'd say that's my best go-to here. So, copying and pasting the graph, let's identify a couple points on here so we can know for sure what we're dealing with. We have a y-intercept of 1. Y-intercept of 1, that should be our b value, our a value. And our b value should be based off our decay rate. This thing goes from 8 to 4 to 2 to 1, etc. as x increases by 1. So the b value should be 1/2. We're dividing by 2 each time. So our equation is going to be f of x equals 1 times 1/2 to the x power, or just 1/2 to the x power. Use parentheses around that guy. If I want to find f of negative 7, I have to substitute negative 7 for x. Now, a negative exponent means I get to flip this fraction and raise to the 7th. That's the same thing as 2 to the 7th power, which we saw earlier as 128. And that is the y value. What you can also do is, this is at 8 right now. When you go to negative 4, you double it again, that's 16. Double it again at 5 is 32. Double it again at 6 is 64. Double it again at negative 7, is positive 128. All right, those looked like things that would have been from this last chapter. Let's see what they do with the previous chapters. Number 3. Student A claims he can form a linear system, chapter 5, linear system from the equation shown that has infinitely many solutions. Student B claims she can form a linear system from the equations shown that has 1 solution. Student C claims he can form a linear system from the equations that has no solution. Select 2 equations to support student's A claim for part A, student B for part B, and C for part C. For infinitely many solutions, they need to basically be the same equation, but just a manipulation of them. I'm going to start with this one and see if I can find a link of another one that works, meaning it's the same thing, but just like double everything or triple everything or something like that. If I triple, that does work. If I swap these around, see how they're swapped around? All of these numbers are times 3. 3x times 3 is 9x, y times 3 is 3, and 12 times 3 is 36. That means it's the same equation but tripled, and if it's the same equation, it has infinitely many solutions. This might not be the only answer, but this is one of the answers. 3x plus y equals 12. They don't ask me to explain, so I'm just kind of saying it out loud for you. And 3y plus 9x equals 36. So there's one support student A's claim. Student B, I just need two equations that aren't the same or whatever. Like, I think these two should be just fine right here. Y would equal 0 when I substitute, or, when I use the elimination method. So these two would work just fine right here because they're different. They don't have the same slope, basically. If I got y by itself, they'd be different slopes. I think that's just the best way of talking about that. So I'm finding the first ones I can. Now, C's claim is something where I need x and y to be at the same growth rate with each other, but then the constant needs to be different so that when the variables cancel, you don't get 0 equals 0, you get 0 equals a non-zero number. So can I compare this with one? See, if I double 3x, I get 6x. If I double y, I get 2y. Those work. And if I double 12, I'd get 24, but this shows a 6. So these would be ones that if I multiplied that one by -2, the x's and y's would cancel, but you get something on the other side. So to support C's claim, this would be a no solution case. Same slope, different y-intercepts. So I'm going to go ahead and use those ones. I'm sure there are other, I'm not positive, but I'm sure there are probably others if you seek them. I just went with the first one, compared it, and I found them. Okay, number 4. Fill in the inequality with less than or equal to, greater than or equal to. So the system of linear inequalities has no solution. So y minus 2x is less than or equal to 4, and 6x minus 3y compared to -12. Lots to talk about here. What I probably just need, I don't want an overlapping shaded region. So when I consider, and these are both in standard form, and I can use standard form to make these graphs. I think seeing the graphs are completely valuable to what we're going to do here. So if I construct these graphs, the first one, it has an x-intercept of -2 if you divide both sides by -2. It has a y-intercept of 4. It has a solid line, in case that matters. It has a solid line, and the shading is based on testing a point like 0, 0. I believe when you test 0, 0, you get 0 is less than or equal to 4, which is true, which means we should shade underneath this line. So we shade underneath this line. I'm not going to make it perfect looking. I'm just going to make it decent enough. So there's shading underneath. I need to make sure my other graph doesn't have an overlapping shaded region that matches this one. So my next graph here, divide by, oh, I see. Divide by 6, you get -2 for an x-intercept, same as this one. Divide by -3, you get a y-intercept of 4. So they share the same x and y-intercepts. So how is it possible for us to have no solution when they share the same line? This line has to have a dotted boundary line. So it was important for me to mention the other one was solid. This one needs to have dotted, because dotted with solid means that's not a solution to the system. Only solution for the solid one, but not the dotted one. And I need to shade above this line for this to represent a no solution case, because shading above is one where these would never intersect there. Now, if I tested 0, 0, this would say 0 blank -12. If I shade above it, 0, 0 is not a part of the solution set. I want this to be a false answer. So I want this to say 0 is less than -12 in that case, to be false, which is what we want, because 0, 0 shouldn't be a part of this solution set for this dotted line here. It's not less than or equal to, it's just less than. So this answer here is less than. Less than, less than, less than. Less than doesn't always mean shade underneath. That's only when it's y, slope-intercept form, when you compare y to the things. But since we're in standard form, different things happen in this situation. Okay. So I'm gathering it's a less than. Number 5. The second term of a sequence is 7. Each term of the sequence is 10 more. than the preceding term. Fill in values to write a recursive rule and an explicit rule for the sequence. So it's clearly arithmetic, and because they're using recursive rules, that means it has to do with our current chapter, chapter 6. Although we did do arithmetic sequence explicit rules back when. I don't remember the chapter still. I'm just drawing a blank. It might be chapter 4. Might be chapter 5. I don't know. So here, the second term is 7. Okay, interesting. They didn't say the first term. So the second term is 7. The first term we don't know. And each term is 10 more than the preceding term. So plus 10, which means if we add 10 to get 7, we'd subtract 7 to figure out that that number is negative 3. So the first term is negative 3. Now, this part here, you add 10 more than you did before, so this is the recursive rule. This one's going to be a little bit different here because what you have to keep in mind is that this is the simplified form of what we have. So for an explicit rule, we start from negative 3 and add 10 n minus 1 times, but notice after you do distribution and such, you actually get a number that's even 10 less than negative 3, which you end up getting negative 13. Take a look at this. So 10n minus 10, which is 10n minus 13 when you combine those. So this is 10, and that's negative, well, that's 13 right there. So those are the numbers that we'd fill in. All good to go. 4 more questions. Number 6. A data set consists of the heights y in feet of a hot air balloon, t, minutes after it begins its descent. An equation of the line of best fit is y equals 870 minus 14.8t. It's kind of slope-intercept form. It's just written in a different order. Which of the following is a correct interpretation of the line of best fit? Well, here's what I will say. I will rewrite this in slope-intercept form so we get the appearance of, this is the slope, this is the y-intercept. My interpretation is you start at 870 feet. You start your descent at 870 feet. That's where it begins. And then you're losing 14.8 feet per minute. It's descending 14.8 feet per minute. So let's see which one matches that. The initial height of the hot air balloon is 870. Check. Well, is the initial? Yeah, sure. The slope has no meaning in this context. No check. There's definitely meaning for the slope. The initial height of the hot air balloon is 870. Check. And it descends 14.8 feet per minute. I believe that's also check. That one looks good. Let's make sure it's not any of the other two. Initial height is 870 and it ascends? No, because it's a negative slope. Hot air balloon descends 14.8 feet per minute. Y-intercept has no meaning. It does have meaning, so it looks like it's going to be B. So again, descending 14.8 feet per minute starts with an initial height of 870. Number 7. Select all functions whose x value is an integer when f of x equals 10. Notice they're not saying f of 10. You're finding the value of x when you get 10. So let's try it for several of these here. We have 10 equals 3x minus 2. I add 2 and I divide by 3. I get x equals 4. That means this one is all gravy. That's an integer. Let's try it again. Let's do 10 equals negative 2x plus 4. We subtract 4. And we divide by negative 2. You get x equals negative 3. Also an integer. So this one's good. Substitute 10 here for y. 3 halves x plus 4. Subtract 4 here to get 6. Now, dividing by 3 halves is multiplying by 2/3. So times 2/3 here and here. 6 divided by 3 is 2. 2 times 2 is 4. So x equals 4. So far, the first 3 all look good. Right there. Let's check out the next 3. We have 10 equals negative 3x plus 5. If I subtract 5, I get 5. And that one is negative 5/3. So that one's no good. On the next one, I get 10 equals 1/2 x minus 6. Add 6 to both sides. You get 16. And multiply by 2, right? That's what we're going to do here. Is that's x equals 32. Totally an integer. A lot of these work. Only one of them is going to be an outcast, huh? Maybe this one as well. 10 equals 4x plus 14. Subtract 14. Yeah. Oh, no. This one actually does work. And you get x equals negative 1. So x equals negative 1 is good. So the only one that doesn't work is the negative 3x plus 5. If that was a minus 5, it actually would have worked out. But nope, not here. So these are checkity, checkity, checkster, checkity, checkster. I meant to do that in green, but that's okay. And this is It's not okay. I need to do this in green. Checks are green. We know this. This is valid information. Number 8. Number 8. Place each function into one of the 3 categories. Ooh, the only reason I don't like these is because I like to reconstruct this whole table, and it generally ends up not doing really well for me. So I'm just going to copy and paste the table, but I am going to write them in myself, I suppose. State whether the functions are exponential, growth, decay, or neither. Now, they are functions already written out, so that should be able to help us. Excuse me, wait. 4 exponential functions state whether they're growth, decay, or neither. I'll put a G or a D for them. All right, first one is totally an exponential function right here, and it is growth because the 8 is more than 1. So f of x equals 2 or negative 2 times 8 to the x power, and it's exponential growth. This one is a quadratic equation. It's neither linear nor exponential, so I'm going to write that as f of right here. F of x equals 6x squared plus 9. This is an exponential function, but this time it's decay. 3 times 1/6 to the x power. This is decay on that one. 1/6 is less than 1 there. This is a linear function. It's almost slope-intercept form. It's 15 minus x, or negative 1x plus 15. So it's a linear function. This one's still exponential. I mean, there's nothing wrong with it having a 2 there. You have to make sure that you'd be squaring 1.6, though, to represent true exponential growth. But it is exponential growth all the same. So this is f of x equals 4 times 1.6 to the 2x power, which is exponential growth. Hopefully those are the only ones that are exponential because I ran out of room. This one here, when all's said and done, if I simplify it, that's negative 3 times 3x plus 1, or negative 9x minus 3. That is totally linear. So negative 3 times 4x plus 1 minus x. 1/2 times 3 to the x power is exponential, so I kind of don't have the room here. 1/2 times 3 to the x power. 3 is more than 1, so it is growth. Okay. The next one, if I distribute this x into here, I actually get 18x minus x squared. X squared is yet again another quadratic, so this is a neither case. So x times 18 minus x is a neither case there. The last one, f of x equals 2. This is one where it's a straight line, but it's a constant function. We don't call it linear, we call it constant. So that one's neither for that reason. I don't think they say explain why if it's not, but that's our neither case there. I don't know. I guess it's linear. I'm thinking about it. I don't want to overstate something. They stress so much that there were constants before. I wanted to state that there. You know what? I'm going to call it linear. It does have a slope of 0. I feel like there should be more linears than neithers. I was kind of in between. I'm going to call it linear. It's a constant function, but it makes a line. So we're all good. Sorry about that. Okay, last one, number 9. How does the graph shown compare to the graph of f of x equals 2 to the x power? Well, this one's a little tricky. Let's learn it. So first thing I'm going to play with is this shift. Notice that there's no horizontal asymptote on the x-axis. Seems to be on the line y equals 3, which is the first thing I can kind of play with there. So instead of being, down there, it's up here. So we have a k value of 3, which is important. Now from here, the doubling effect is still happening. Values are doubled, but if I want like my reference point to be 1, like this one right here, instead of a y-intercept of 1/2, I have to shift this thing over 1 as well. So my h is going to be 1, but my k is going to be 3. And remember, it's an x minus h equation, and we're doing it from that function. So my g of x equation, if you call it this, is taking f of x minus h plus k. So that's going to look like g of x equals 2 to the x minus 1 power plus 3, like that. Now, how does it compare to f of x equals 2 to the x power? Well, this shift and this shift. The graph of g is a horizontal translation, 1 unit to the right, and a vertical translation, 3 units up from f. And that's how we can say that. That would be my final result there. A lot of these ones were, even though they say cumulative review, there was barely anything from some, there's some things from the other chapters, but this was still a lot of chapter 6, right? And that's a good way to close this one off. And guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. And remember, this is the end of our algebra stuff. That doesn't mean we don't have algebra things to do. We're still going to solve for x here and there. That's fine. But we're learning it through different modalities. So statistics for a chapter and then geometry the rest of the way. So get ready for that stuff. And then you hit IM2 and then you go back to algebra full bore again. And I have videos for you on that too. Thank you guys so much. Take care. I'm going to see you in the next one.